right, so we're going to do average rate of change. So this section and the last section are just kind of like calculus light. Here we're going to teach you how to find the average rate of change. And last section we taught you where it's increasing and decreasing. So all of this is stuff you will do with derivatives to find extreme points and max values and all this other stuff. Or the difference between the average rate of change and derivative is instantaneous rate of change. So hold on, somebody's blowing me up. Let me turn on my do not disturb. Whoop. Yep, turn it on. Thank you. So here, that's the only difference. Is the I'll explain it a little bit more. You just take the average rate of change and bring it in closer and closer until it becomes instant radius state change, and that literally is the definition derivative. So let's do this. So the average rate of change is the change in f over the change in x. Notice this is a lot like your slope, the rise over the run, right? So the change in f over the change of x, or f of a minus f of b minus f of a, or b minus a. Once again, if you switch which way you go, it ends up being the same. The average rate of change is the slope of the secant line between a and b, where the line passes through f of a, f of a, b, f of b. Let me kind of just draw this for you. So let's pretend we have, oops, let me make sure it's a function. Function like this, right? And say I took a point here and called this, according to this, I'm calling this A, and I take another point here, and I call this B, right? Well, let me not make solid lines. Let me do a little A, and B. And so this point right here would be A f of A, whatever that function value is. And this point right here will be A or B f of B. Let me draw in this kind of pink just so I use a different color. Let me fill it in a little bit more. And this right here is the secant line. And the slope of this line, the slope is here. The slope of the secant line is equal to the average okay. So here we're going to draw a secant line through the 2 points. And the slope of this line is the average rate of change of the function between A and B. Now, what do you do in calculus? I'll just briefly show you what you do in calculus. What you do in calculus is you slowly bring, here you're going to have 2 points here. You're going to take the secant line, that's the average rate of change. And then you're going to say, okay, let's get a little bit closer. That's the average rate of change. And you get a little bit closer. That's the average rate of change. Until you get the points almost on top of each other. And then instead of the secant line, you're going to have a tangent line at that point. So the only thing you do in calculus is you're going to bring these points excessively close to each other. In fact, you're going to take the limit as the distance between those points go to 0, right? Where h is the distance between the 2 points. It's literally what you're going to do. And that's in calculus. That's what you're going to be considered your derivative. We're not going to do that in this class. That's your calculus class. But we're going to do the secant line and all this stuff. So here's just all the preamble to get you ready for calculus. All right, so calculate the average rate of change for our function here. So we're going to let f of x be x squared, x minus 2 squared. Sorry, let me be clear about that. What does it say after the equal sign? Oh, let me go. The slope is equal to the average rate of change right here. That's what it says, average rate of change. Okay. Is it just me or can't see? Okay, hopefully all that works in text. Okay, everything seems like that. All right, I'm just reading chat. Yeah. All right, so here, let's go down to here. So the slope of the secant line is equal to the average rate of change. So that's what we're doing here. All right, so here, let's just calculate a couple of these. How do we calculate these? Well, we just find 2 points. So there's 2 ways of doing this. One, you can just use the formula I've given you right here. Which is what we're going to do this time. So here we're going to have, so let's go ahead and do this. Somehow, something went horribly. Here we go. So we're going to have f of b, and write it down here, minus f of a all over b minus a. So this is our average rate of change. In this case, I'm going to call this a, I'm going to call this b. And so it'll be f of 2 minus 2 squared. Hold on. Yep, there we go. Minus f of 0 minus 2 squared all over 2 minus 0. Notice every time everywhere I see the x, I'm going to just plug in these values. All right, so 2 minus 2 is 0, so 0. So this becomes 0 squared minus negative 2 squared all over 2 minus 0. And if I simplify that a little bit more, I'll get minus 4 over 2, which equals minus 2. So minus 2 is our average rate of change for this function between the values of 0 and 2. Okay. All right. Let's do this. Or the average rate of change. Yeah, with negative 2. Here, we're going to do between 3 and 6. And so here we'll have, we'll plug in a 6 minus 2 squared. And notice every time I plug something in, I'm going to put it in parentheses. A, I find it kind of useful for teaching, so you know this x is replaced with this 6, right? And B, I find it useful, so I make sure to distribute my negative signs and do what I need to do this correctly. Okay? Over 6 minus 3. Simplify that. This will be 6 minus 2, so it'll be 4 squared minus 3 minus 2 would be 1 squared all over 3. So that's 16 minus 1, so it'll be 15 over 3, which is equal to 5. Okay. All right, so um let's look at this real quick. I want to look at this in Cosmos. So here we go. So here I have x minus 2 squared. Um, see if I can draw this line real quick. This would be negative 2x plus 4. Okay, so here is my secant line between 0 and 2, right? And so here, the slope, the average rate of change, even though if you notice here, the rate of change is quite different. Here it's much greater, and here it's a little bit less. Here it's about 1. Here it's about, minus 3, right? And so here, the rate of change is doing, but the average rate of change for this function between 0 and 2 is negative 2. So it's negative 2 to here, negative 2 here. So we're just taking the average. What you're going to do in calculus is you're slowly going to pull this number in. And for the other one we did, it is 5x trying to calculate how to do this in my head. I need to be at 1. Hold on. Minus 14. Yeah, that's it. I'm solving the equation in my head. So between here, between 3 and 6, the average rate of change here is 5. And so it's this much stronger line here. Okay. And so for any given function, depending on which 2 points, you're going to have different secant lines. All right, so let's put this off to the side. So I just wanted to kind of show you live one of them. All right, so let's go to the next page. Whoop. All right, so here's almost a physics question. So we're going to do average rate of change for kind of 2 different situations. And then we're going to do another function. So here, the average falling rate of a speed of a distance travel is given by this. Distance equals this. This is usually in feet squared, right? Pretty sure this is in feet. Because if it's meter per second, it would be a different number up front. All right, so calculate the distance traveled by an object. So this is the formula. And so we just want to know how far it's fallen. Okay. So we're just going to use this formula and plug in these values. And so we're going to let this be A, let this be B. So be f of B minus f of A all over 2 minus 1. So here it'd be 2, or hold on. Let me not skip ahead for this. Let me just write A minus B minus A. All right, so here we're going to plug in 2. So 16 times 2 squared minus 16 times 1 squared all over 2 minus 1. And so this is why I write it here. I notice that this is in seconds and this is in feet. And so the average rate of change will be feet per second, right? So the distance here given in feet is given by this. So the average rate of change is how many feet per second. Okay, just based off of what we're using here. So this becomes 64 minus 16 over 1. This is still feet per second. Let me write what this is. The distance traveled by an object is, I'm going to write feet right there between. So if I simplify this, that would be 16 minus that would be 48 feet per second. And so the average rate of change between 1 and 2 seconds is 48 feet per second. Because at 1 second, I've traveled 16 feet, or I've fallen 16 feet. I guess this is just someone who stands at the edge of a cliff and just drops a little, drops a penny. Whee! Right? So, and the distance here would be in feet. This is assuming a lot of things like no wind resistance. All right, so let's do what you'd probably do in calculus. This is what you probably do in calculus. You have A, and then you go to A plus H. And so this is my A, and this A plus H is my B. And so let me just show you what you do. So here you plug in your formula. So it'll be 16 A plus H minus 6 or squared, sorry, minus 16A squared all over A plus H minus A. Okay, well, A plus H minus A, well, the A's cancel each other. Here, we'll go ahead and FOIL this. So it'll be 16A squared plus 32AH plus h squared, because a plus h squared is a squared plus 2h, or 2ah plus h squared, and then we multiply that by 16, so we get this, minus 16a squared all over h, and then here we can just cancel out this, and that leaves us with 32ah, oops, I forgot my 2, didn't I? Ah plus 16h squared all over h, and then here I can cancel out an h. Since I have an h in each term, I'll cancel out an h everywhere. And so we usually just cross off the square here. We get 32a plus 16h. Okay. And so this is the units on that will still be feet per second. Okay. And this is what you do in calculus when you're finding the derivatives. The only difference here is that you're going to set take the limit as h go to 0, and this one just becomes 32a. Okay. Don't worry about, I'm trying to give you guys a little glimpse of what's happening in calculus, and some of you've taken calculus, so you can kind of see what this is. But if you don't understand that, that's fine. Just make sure you understand how to find these values. Okay. All right. Let's do it for another function. Here's a linear function. And the reason I want to show you for a linear function, so here, let's go ahead and do this. It'll be 2, 8 plus 4 minus 2 times 3 plus 4. So here, I'm plugging in the function value here and the function value here, minus 8 minus 3. So 2 times 8 is 16 plus 4 is 20. So this will be 20. 2 times 3 will be 6 plus 4 is 10, minus 10 all over 5. So this is equal to, this is 10 over 5, so that's just 2. Here, if we do a plus h, so let's just have 2 times a plus h plus 4 minus 2a plus 4 all over a plus h minus a. So a plus h minus a, to make it a little bit more clear. Here the a's cancel. So we have 2a plus 2h plus 4 minus 2a. Carry in the negative, minus 4 all over h. Here we can cancel out 2a's. We can cancel out the 4's. And then here we're only left with an h over 2h. So just 2h over h. Cancel that out, and we get 2. Now, does that make a whole lot of sense? And it should, right? What's the average rate of change of a this is linear, right? This is linear of a line. The average rate of change of a line is the slope, right? And the slope of this line is 2, right? So it doesn't matter if I go from 3 to 8 or from a to a plus h, it's always going to be 2. Okay. So the average rate of change for linear things are constant. It's a very fancy way of saying the average rate of change of a line is a slope. Anyway, for those who take in calculus, you do know you do this and this a whole bunch. So, all right, let's do our little last page right here. So let's look back at our happy graph of temperatures, right? And so here we want to calculate the average rate of change between the following things. And the reason I show you this is that sometimes average rates of changes are good in their context. And let me explain what that is. So here from June 28th, we're going to find the average rate of change between 6 a.m. to 6 p.m. So we're going to start here and we're going to go here, right? I'm trying to draw. So this right here would be kind of my line for this one. And so if I did that here, I'm going to say this is roughly, if I could read this, this is roughly 95 degrees roughly. 95 degrees roughly. This will be 70, 7 degrees. All over here, that's a 12-hour span, right? So here, the difference between 6 a.m. and 6 p.m. would be 12 hours. Okay. And these are given in degrees F. So these are in Fahrenheit. So here, a gram of fire would be 18. Yeah. So 18 degrees F over 12 hours. I'm trying to do mental math. If I do something wrong, isn't that? You were right. You guys are right. I'm doing this for the wrong one. This is the 27th. Let me grab the right data. Here, we'll have it from here to here. All right, so for that, let me just fix this real quick. It's still 12 hours. But we'll say that's about, we'll make this 98. We'll make this, say 74. So that makes this the difference of 24 degrees Fahrenheit. Oh, that makes the math a lot easier. Then this becomes 2 degrees F per hour. Okay. So, thank you for pointing that out. So this is 2 degrees per hour. So here, so this average rate of change says on any given day between while the function's kind of increasing, you gain about 2 degrees Fahrenheit for every hour. So if you had to go work on your car or something, and it's like it's kind of warm outside, you're like, well, I'll wait an hour, and you're like, well, that's 2 degrees hotter. But if you wait like 3 hours, that's 6 degrees hotter, right? And so, it's useful information to have. And since this is for Vegas, it's not completely bogus. So let's do from 11 a.m. to 12 p.m. And so here we're just going to do from 11 to 12. So from here, here. Oh, wait a second. Then we route from here to here. I'm just going to say this is roughly because of the. Yeah, so this would be roughly 96 degrees. This would be roughly 95 degrees. And these are estimates, of course. And here, the difference here is 1 hour. And so here we have about 1 degree F per hour. And so notice here, it's increasing quite a lot, and then it kind of levels out as we get towards the midday section, and then it decreases again. All right, so let's do from 5 p.m. to 5 p.m. from the 27th to the 5th. So let's do this in, I'll go ahead and do this in a different color. So here we're going to do about 5 p.m. So that's about here. And about like an aim here, I suppose, right? And so here's the secant line. So we'll say this is say 100 degrees, roughly at 5 p.m. We'll say this is at 98 degrees, roughly. And this is for 24 hours, right? Now, if I write that, this becomes roughly 2 over 24, or 1/12 of a degree F per hour. But is that a good estimate, or at least a good way of stating this estimate? Is I gain 1/12 of a degree Fahrenheit per hour? No, right? But if I rewrote this as 100 over 98 over 1 day, right? My change of x is 1 day. I said I gained about 1 or 2 degrees Fahrenheit per day. That makes a little bit more sense because that means as we go further and further in the summer, it's going to get a little bit more warmer and warmer. Okay, so while this average rate of change is not very useful in writing it as per hour, but if we write it as per day, tells you how things go from day to day. So when you use average rate of change, just be kind of clear um, what your purpose is and what you're going for. And so let me just do this one right here. So this is between 11 a.m. and 12 p.m. So it's this point here and this point here. I'm going to say roughly this is 93 and this is 92. So here would be 92, which is my further point in the x, minus 93 over 1 hour time span, so 1 hour. So this is minus 1 degree Fahrenheit per hour. And so when it rained, you got minus 1 degree. So as engineers, you may have to look at real graphs to figure out average rates of change and then approximate, derivatives and all this other stuff from graphs. And so this is just give you some practice on that. All right, so that's the end of the notes, not only for this section, but for this week.